Okay, today our meeting have guest speakers, Denis Mazur and Artyom Eliseev. They published very interesting work, and it really enables you to run Mixtral model, which is one of the top model, my favorite model. I use it every day, but now you can run it on the laptop. Thanks for your work. Guys, you have the floor. Go ahead.
All right. So hello. We are Denis and Artyom. We studied MIPT, work at Yandex, and today we will be presenting our work on efficient inference of mixture of expert models, specifically Mixtral. This talk will require you to be familiar with large language models in general, and you would need to know a little bit about transformers. We will give you a brief introduction, but we do hope you are familiar with those concepts. So let us begin. I think we mixed up the order of those slides, but never mind. So what is a language model? A language model is a kind of machine learning model, a statistical model that predicts the next token in a sentence. A token can be a word or a character based on the beginning of a sentence. So basically give it a prompt, a beginning of a sentence, and it predicts you the next word, the next character, whatever your token is. And this task is called language modeling. There are a lot of different ways of solving it. You can use LSTMs, you can use naive Bayesian models, whatever you want. But the most popular architecture for this task is the transformer. They've been around for quite a while, but they are only getting more and more popular. We won't get into the nitty-gritty of what a transformer model is, but the things you need to remember is that they consist of two basic building blocks. The masked multi-head attention, and the feed-forward layers. The multi-head attention is the base mechanism that makes the transformer work. It basically, you give it a token and it looks at the rest of the tokens in the sentence and pays attention to the tokens that need to be attended to. I won't get into the details. And the feed-forward network basically stores all the knowledge of the transformer. If you would like to learn more, there are plenty of great materials on the internet. So most of the transformer's knowledge is in the feed-forward network, and they can get quite big. They can get really, really big, and they become hard to inference. And one way to mitigate this problem is mixture of experts. Basically, what you do is take your big FFN layer, feed-forward network layer, and split it up into little experts and create a routing layer. And every time your routing layer sees a new token, it chooses only one of those experts. And your inference becomes much cheaper, but the model can basically store the same amount of information. So here on the slide, you can see an example. First, the router sees the token we and decides it chooses the second expert with probability 0.65, and then it sees the like token and chooses a different expert with a different probability. So here we arrive at Mixtral. Mixtral is a mixture of experts model made by Mistral AI, a French startup. It's huge. It's really big. It's 47 billion parameters. That's a lot. But despite being smaller than the competition, despite being smaller than, for example, Llama 70 billion, Llama 2 that has 70 billion parameters, it outperforms it and a lot of other open source models on various benchmarks. For example, the MMLU benchmark. It's a great model. If what I have said doesn't make you want to run it on your hardware. I don't know what will. But despite being open source, it's not really possible to run it on consumer-grade hardware because it's really big. It simply doesn't fit into your hardware without tricks. And today we will be talking about those tricks, basically. So, and I'll figuratively give the microphone to my colleague, Artyom, who will be telling you the first part of our method, mainly quantization. Artyom, please.
Thank you, Denis. So, quantization. As Denis said, the main problem of inference in large language models is their size, because mixture of experts solves the problem of speed, because we don't need to inference all the parameters of the model now. We need to inference like quarter of the parameters each time. But we still need to store all the parameters on GPU. And Mixtral model is very, very big. So we want to somehow compress it. And quantization basically does this. Quantization compresses parameters into lower precision data types, for example, from floating point 16 into integer 8 bits or 4 bits or even 2 bits. This not only reduces the memory footprint of a model, but also speeds up the inference a little bit. So it's very useful for us for inference on a resource-restricted hardware. As you can see from the figure on your right, on the x-axis, you can see the total model bits. It's the total model size. And on the y-axis, you can see model accuracy. It's how well the model performs. So given the fixed model size, we can see that it's best to quantize the model. So do not store it in floating point 16, but to store it in, for example, integer 4 bit. But as it comes to 3 bits or even 2 bits, things can get a little bit tricky, and the accuracy is not very stable. So we didn't quantize all the model in 2 bits because it would be very bad. Instead, we experimented with different quantization schemes. For example, we quantized attention and experts in different setups, while keeping the rest of the model, like head and embeddings, in floating point 16. And we found that the best step is to store attention in 4 bits and experts in 2 or 3 bits. Attention is more sensitive to change, and experts actually use almost 97% of parameters of memory. Also, we used HQQ. It's high quadratic quantization. It's a new quantization method, not from us. We used it because it's quite good for 2 bits quantization, and also it's very easy to use. So, yeah. And now Denis will tell you about our second trick. It's offloading. Denis, please.
So, if you look at the table on this slide, you can see that the quantization setups we chose, and in this setup, we have 21 gigabytes of memory for the experts only. And imagine you bought a 3060 Nvidia GPU. It's quite a good GPU. It's consumer grade. It's not too expensive. It's like $600. I just looked it up on Amazon. But the problem is that your 3060 GPU only has 12 gigabytes of VRAM, and that's not enough to fit the whole model. It's not enough to fit all the experts in the VRAM. But you also would need more memory for attention layers, for activations and stuff. That's a problem. But when you're inferencing a transformer model, you don't need all of the parameters at the same time. You're usually doing it layer by layer, decoder block by decoder block, and you only need one of those. So what you can do is take the decoder blocks you're not using and put their parameters on CPU memory. And usually you have more CPU memory than a GPU memory. And that way you can fit the whole model into VRAM plus RAM and run it that way. And as soon as you need parameters for inference, you just unload them onto GPU memory, do your calculations, and offload them back. So there's a demonstration of that on the right. For example, let's say we're inferencing the ith decoder block. It is on GPU memory, and we have preloaded the next one, but we've already inferenced the previous one, so it's on CPU, and we haven't loaded the others yet. This is how offloading is usually done. I remind you that transformers usually don't have different experts. They just have one FFN layer, and you need all of those parameters to compute an activation of a decoder block. But Mixtral is a mixture of experts model. And when you're inferencing a mixture of experts decoder block, you don't need all of those parameters. You only, if we're talking about Mixtral, you only need 2 experts per inference per layer, which is shown on this slide. So for example, our gating layer shows experts 1 and 2. They are unloaded onto GPU memory, and the rest just stay on CPU. And it sounds like a quite obvious trick. And you might ask, why doesn't everybody just offload their parameters to CPU? And the problem is that as soon as you start doing that, memory bandwidth becomes a problem. So it becomes really expensive to move tensors from GPU to CPU back and all the way around. So we need to find a way to optimize those memory, how do you say that? Well, we want to offload and unload as little as possible. Turns out it is possible in mixture of experts. So let me explain you the diagram that is on the slide right now. On the x-axis, you have different tokens, and on the y-axis, you have different experts. And the blue squares, they show you the gating function activations. So on the token chat, the 15th gating layer chose the 5th and the 7th expert. And as you can see, experts are often reused between adjacent tokens. You can see it here, you can see it here, you can see it here. And what we can do is put our experts into a least recently used cache. And as soon as we need more space to load a new expert onto GPU memory, we just simply throw away to the CPU memory the least recently used expert. And I don't have the numbers here, but I have them on the last slide. It speeds up the inference. It speeds up the inference. So here's caching in action, basically. Before we apply the gating layer to the input, we have the first and the second expert in GPU memory. the gating layer selects the second and the third experts, and they are unloaded onto GPU, and you do your inference. Great, but that's still a bit suboptimal. It's a quite popular program in computer science in general, not knowing what will happen. Moving stuff between memory is expensive on CPUs, in data centers, everywhere. And usually it is solved by speculatively loading stuff while you're doing computations. And we apply the same trick to our model. The thing is to Mixtral. So the thing is that there's a thing called residual streams and transformers. These are those things. You apply a feed-forward network or an attention module to the inputs, and then you add the results to the inputs. That's called a residual stream. And because of those residual streams, the input of a decoder block doesn't change too much during computation, and they are quite similar. So what you can do is take the activations from a multi-head. You can take the activations from the ith layer, feed them to the ith gating layer, and you will definitely use those experts. But you can also speculatively feed those outputs to the I plus first gating layer and speculatively load some experts into memory. And they are loaded while you're doing the computations. So those overlap, and you save quite a bit of time doing that. I hope you did understand this explanation. We can get into a bit more details after the presentation if you have any questions left. So I'll kindly ask Artyom to tell you about the results we have.
Yeah, thank you, Denis. A few words about results. First of all, we managed to speed the inference up like 4 times on almost all GPU presented. In details, simple LRU caching gave us almost times speed up. It's because if you look at the figure at the top left, you can see the cache hit rate per layer. So if we have cache size of 4, it's the red line. We have around 65% cache hit rate. Basically, what this means, that means that whenever we need to use expert, there's a 2/3 probability, like 65%, that it will be already on GPU, simply because of LRU caching. Next, we have prefetching. Like Denis said, it gives also around 2 times speed up, a little bit less, actually. As you can see from the figure at the top right, if we manage to fetch 2 experts and load them while we are computing the previous layer, there's a 80% probability for each expert that it will be already loaded to the GPU when it will be needed. So I think that's quite good. That's quite good. In conclusion, I'd like to sum up everything we have said. So large language models are big. They're good at language modeling, but they're huge. And to inference them on hardware restricted setups, we need to somehow compress them. And we propose a mixture of experts specific offloading strategy and also mixed quantization, which almost speeds up the inference almost 4 times. And using these techniques, you can run Mixtral, which is a very good language model, on Google Cloud or on your laptop with a decent speed and quality. I think that's all. If you have any questions, we would be glad to answer them.
Okay. Well, first of all, it was very good. Thank you. And it's very elegant work. I really like it. So, Dima? Oh, okay. Oh, here you are. So Dima has two 3090s in his desktop. So I guess he can run Mixtral using your code, right?
That's a tricky one. I don't think it's possible using our code because our code was specifically written for a one GPU setup.
Yeah, we can use
It's
just
a
one.
bit hard to explain why, but there's this thing called storage and in PyTorch, and it isn't meant to be managed manually, but we do manage it manually. But the thing you can do is quantize it and try running it tensor parallel. There's a great library for doing that. I can send you a link.
Yeah, please do. Interesting. So once you start, the model is between computer system memory and GPU, and it goes back and forth, never landing back to disk, right? So you're not swapping to the disk. You just...
No, we're not.
Yeah.
Right. Oh, okay. Guys, any more questions?
Yeah, I have a question. Yeah, can I ask?
Yeah.
I only started learning LLM, so maybe my question a little bit simple. So let's say I have RAM, big RAM, 128 gigabyte, and I have very modest GPU, 3060, 8 gigabyte RAM, right? So I would think I can run it layer by layer and keep the rest of the model in RAM without quantization. And I saw some people save a model in a disk, and then really, in spite of it is AMV disk, still a lot of time to read to disk, to write to disk. So is that what you're doing, like without quantization? You save model in a RAM, and then like doing layer by layer of load, something like this? If not, do you know somebody doing like this? So no quantization, only I want to run one layer at a time.
You take
sure
90 something gigabytes and then split it in 32 layers, so it will be about 3 gigabytes at a time, and then you just push it to the... Oh gosh.
Yeah, it's kind of a naive decision. It's I want to try understand, like, why not? And if yes, who is doing?
I'm sure somebody's doing it. I don't know anybody specific, but recently a guy came to our issues, to the issues in our GitHub repository, and he wants to run the model using our code but without quantization. He told us he will be working on it, but I don't know whether he is. So hopefully it will be possible to run our model without not our model, but run our offloading without quantization, but I wouldn't bet on it.
Well, it should be slow, right? Because for each token, you have to go through all 32 layers, and for each layer, you have to offload the previous one, load the new one. It just...
Yeah, absolutely. But that guy is running it in a weird setup. He has a lot of RAM and he has an 800 GPU. So I think he can afford it. He doesn't really need quantization. He could have quantized it in 4-bit without losing much of the accuracy, but he chose to offload it.
But
So,
what is
yeah.
the problem for him? Sorry, if he has 800, he has a lot of RAM for GPU, right? But he needed. It's still not enough. 800.
It's like
his machine has
gigabyte short.
Right.
For Mixtral, A100 is like 5 gigabyte short on GPU memory.
A little bit.
Yeah, just a little bit. Oh.
Good. So in any case, as Lev clarified, you do not use disk. You have RAM and GPU. That's all.
Yeah.
Yeah.
Right.
Offloading to disk would be very slow.
And what is minimalistic GPU would be, even with quantization?
What are the minimum requirements for the GPU?
Yeah.
You did it on 12 gig. Can we do it on 8 gig or 6 gig?
You would need to offload more experts then. It's possible with 8 gigs, I think, but it would be the speed will be god awful.
And it also depends on the context size. So if you want to generate like 30,000 tokens, it wouldn't fit. Just because
No, I'm talking about something like 100 token, 200 token, something small.
8 gigabyte would be enough with less experts on GPU.
Interesting to try. Yeah, sure.
Yeah.
Thank you for the question.
I have a question. So when you use a Mixtral, it already trained, but 8 experts. What about 6 experts? Have anybody tried to use less experts?
Yeah, well, during inference, you mean, or?
No, I guess you need to train the model from scratch, right?
Yeah, exactly.
Right.
We tried inferencing the model with using only one expert, but the quality degrades quite a bit.
Mm-hmm. Okay. Interesting. So
basically, because Mixtral is trained to use 2 experts.
Right. But you know like how to prefetch things from layer to layer, but you also go from token to token inside the layer, right? And you're loading, offloading as you go through the tokens.
Yes.
Yes.
Right. I'm sorry. Can you show again the slide which I edited and you didn't show?
Yes, of course.
Which shows all the champions of large language models. Yes, this one. Because this is the latest. You see the date on this is today. Right. And you see the Mixtral is on number 8 in this list of champions. And Bard is on the 2nd place, which is new because it was like below. You see GPT-4 is going strong, Google Bard, Mistral Medium, but Mistral Medium is not open source.
Yes.
Claude, also not open source. And then Mixtral, which is model you worked on, is number 8, and this is the best top open source model. And you showed how everybody can run on their laptop or desktop, well, with reasonable requirements, which is great. I think this is very useful. I think many people can take advantage of your work. Yeah, this is great. Guys, have you heard of Mamba?
Yeah, we have.
Yeah.
Yeah, are you planning to do something with it?
Wait, how many parameters is Mamba, by the way?
Well, the one in the paper is 2.8 billion.
I think it should fit onto your Mac, doesn't it?
Yeah, probably. And I just wonder because I haven't seen any research which would compare, given the size of the model, the transformer and member. But
Isn't that what Mambus paper is about, basically? They do have a
they did it,
comparison.
but they, yeah, on small models, not real situations. So we'll see.
Does the paper compare itself to transformer models of a 2 billion
Yeah,
scale, or does it not?
It does. Anyway, guys, let's stop the recording for now, right?
Right?
Yeah.